Welcome to another deep dive. Today we'll be exploring a really interesting mathematical concept,
Yeah.
the Euler characteristic, and basically it's a number
Okay.
that can tell us about a shape's structure,
Right.
kind of like a fingerprint for a shape.
Yeah, and the cool thing is it doesn't matter
Okay.
how you bend it or stretch it or twist it around.
Yeah,
It still stays the same.
that is pretty cool.
Yeah, it's all about the topology.
Okay, so to guide us on this journey,
Mm-hmm.
we've got excerpts from a couple sources.
Okay.
A history of the Euler characteristic,
All right.
and of course the Wikipedia article
Sounds good.
on Euler characteristic.
Yeah, so to jump right in,
Okay.
I think what's really interesting about this is that the Euler characteristic remains the same no matter how much you mess with the shape. Like it captures this kind of essence of its topology.
Okay, so let's start with something simple, something I can visualize,
Yeah.
like a cube.
Okay.
I remember back in geometry class
Mm-hmm.
that it has 8 vertices, 12 edges, and 6 faces.
Does the Euler characteristic come in there?
You got it. So for polyhedra, those 3D shapes with flat faces, the Euler characteristic boils down to a pretty elegant formula. Vertices minus edges plus faces
Okay.
equals 2.
Oh.
Always 2.
Always two. Interesting.
Yeah, so for your cube, 8, 12 plus 6
Okay.
does indeed equal 2.
All right. Yeah, that makes sense.
Yep.
That's pretty amazing that such a simple formula can reveal something so fundamental about a shape.
It is.
Did mathematicians always know about this?
Well, the story goes all the way back to 1537
Oh, no.
with this guy, Francesco Morolico.
Okay.
He noticed this pattern in Platonic solids.
Okay.
You know, those perfectly symmetrical shapes
Yeah.
like the tetrahedron and the dodecahedron.
Right.
But it wasn't really until Leonhard Euler
Ah.
came along that this concept took off.
Okay.
He's the reason it's even called the Euler
I was
characteristic.
going to say.
Yeah.
So did Euler figure out that this formula works for any polyhedra? Well, he tried. Even he had some trouble coming up with a really rigorous proof.
Really?
Yeah, it actually took another brilliant mathematician, Augustin Louis Cauchy, to really finalize the proof.
Wow.
Back in 1811.
It took a while.
Yeah.
From what I've read, though, Euler's work was sort of just the starting point for
Well,
something much bigger.
Exactly.
It's not just about these 3D shapes, right?
Nope, you got it.
Okay, so
It goes way beyond that.
mathematicians realized that the Euler characteristic could be applied to all sorts of more abstract spaces, things like networks or maps,
Yeah.
and even spaces beyond our 3D world.
Exactly.
Okay, that's where I start to lose track a little bit.
Okay.
Can you give me an example of one of those more abstract spaces, something I can at least try to visualize?
Okay, so think of a soccer ball.
Okay,
It's made of pentagons and hexagons, right?
yeah.
The Euler characteristic actually dictates that no matter how many hexagons you use, there will always be 12 pentagons.
Wait, so the Euler characteristic is actually controlling the structure of a soccer ball?
In a way, yeah, it's kind of a hidden rule.
Wow,
Yeah.
okay. But how does that connect to the abstract spaces you're talking about?
So that soccer ball pattern actually gives us a little glimpse
Okay.
into the topology of a sphere.
Okay.
And this same principle applies to even more complex structures,
Like what?
like carbon molecules shaped like tiny soccer balls called fullerenes.
Wow.
But it goes even further than that.
So how did mathematicians go from soccer balls to these more complex ideas?
So they started looking for ways to break down spaces into simpler pieces, kind of like building blocks, like points, lines, squares, cubes, like Legos.
Okay, I like that.
Yeah, and these structures are called CW complexes.
CW complexes. Okay, so instead of counting vertices, edges, and faces, they're counting these building blocks
Yeah.
in different dimensions.
Exactly. And just like with polyhedra, the Euler characteristic gives us a way to kind of sum up the structure of these complexes, no matter how complex they get.
So you're saying this idea that started with shapes we can hold in our hands
Yeah.
is a really powerful tool for understanding the structure of spaces we can barely imagine.
Exactly.
Wow, this is already blowing my mind.
It's pretty amazing stuff.
But I'm ready for more.
All right, let's keep going.
Last time we were talking about how the Euler characteristic can be applied to those Lego-like structures
Right.
called CW complexes.
Exactly.
It's starting to feel like this concept goes way deeper than I initially thought.
Yeah, you're right. It goes way deeper. The Euler characteristic isn't just about shapes, it's
Oh.
about classifying and understanding these relationships between different types of spaces,
Okay.
even ones we can't really easily visualize.
So how does that classification work? Can you give me an example?
Sure. Let's think about surfaces,
Okay.
like a sphere or a donut.
Okay.
What do you think the Euler characteristic of a donut might be?
That's a tough one. I know a sphere's is too, but a donut has that hole in the middle.
Right.
Does that change things?
It definitely does. A donut, or a torus, as mathematicians call it,
Okay.
has an Euler characteristic of 0.
Huh.
And that single number tells us it's fundamentally different from a sphere,
Oh.
no matter how much you stretch or bend them.
So even if I somehow morphed a donut into a sphere-like blob, their Euler characteristics would stay different.
Exactly.
It's like this number is revealing some hidden truth about their structure.
You got it.
Yeah.
It's revealing the underlying topology.
Wow.
And this classification power extends to surfaces way more complex than donuts or spheres.
Okay.
Imagine surfaces with multiple holes, twists, even self-intersections.
Oh, wow.
The Euler characteristic can handle it all.
It's like a universal language for describing how complicated a surface is.
Yeah, that's a good way to think about it.
But you mentioned relationships between spaces, too. What did you mean by that?
All right, so imagine you have a sphere,
Right.
and you cut a hole in it. What do you get?
I guess you'd have something like a bowl shape with a circular edge.
Exactly. That bowl shape is topologically equivalent to a disk.
Okay.
Now think about the Euler characteristics.
Okay.
The sphere's is 2.
Right.
And when you cut that hole, you essentially create a disk with an Euler characteristic of 1.
Huh?
So the sphere's Euler characteristic decreases by 1,
Okay.
which is exactly the Euler characteristic of the boundary you created, the circle.
Whoa. So cutting a hole changes the Euler characteristic in a predictable way.
It does. It's pretty neat, huh?
That's wild.
And this principle applies to more complex manipulations, too. Like if you glued two surfaces together along a shared boundary,
Okay.
you can actually calculate the Euler characteristic of that new surface just by knowing the Euler characteristics of the original surfaces and that boundary.
So it's like a recipe for building and understanding shapes,
Yeah.
using the Euler characteristic as your guide.
Exactly.
But we've only been talking about 2D surfaces, right?
Hmm.
What about those higher dimensions you mentioned before? Does the Euler characteristic apply there too?
Absolutely. Just like we can extend the idea from polyhedra to more abstract complexes,
Okay.
we can extend it to higher dimensions.
Oh.
So a point is 0-dimensional, a line is 1-dimensional, a square is 2-dimensional, a cube is 3-dimensional.
Right.
But we don't have to stop there.
What was I going to say?
Mathematicians explore spaces with 4, 5, or even more dimensions.
I'm trying to wrap my head around that.
Yeah.
It's hard enough visualizing 4 dimensions, let alone calculating something like the Euler characteristic in those spaces.
It's definitely mind-bending, but the math still works.
Huh.
For example, a hypercube, which is the 4D equivalent of a cube, has an Euler characteristic of 0.
Mhm.
And as you go up in dimensions, the Euler characteristic actually alternates between 0 and 2.
So even in those higher dimensions, the Euler characteristic is still revealing something fundamental
Yes.
about the structure of those spaces.
Exactly. It's a powerful concept.
It's incredible how this one concept can connect so many different ideas across mathematics.
It really is. It's one of the things that makes it so fascinating.
Yeah.
It connects geometry, topology, even fields like cosmology.
Cosmology, you're going to have to explain that one.
Okay.
What does the Euler characteristic have to do with the universe?
Well, think of the universe as a vast space.
Okay.
Just like any other space, it might have an Euler characteristic.
Hold on. Are you suggesting we could calculate the Euler characteristic of the entire universe?
It's a pretty wild thought, right?
That's blowing my mind again.
Of course, actually calculating it is a whole other story.
Yeah.
We'd need to know a lot more about the universe's shape and whether it has any boundaries.
Right.
But the very possibility raises some profound questions.
So what would knowing the Euler characteristic of the universe tell us?
Okay.
It's not like we could just hold it in our hands and count its vertices and edges.
You're right about that. But remember how we talked about the Euler characteristic being like a fingerprint for a space?
Yeah.
It captures its fundamental structure. So if we knew the universe's Euler characteristic, it could tell us about its overall shape, how it's connected,
Okay.
and maybe even hint at hidden dimensions we can't perceive.
That's an amazing thought. But we've covered so much ground already.
We have.
Where do we even go from here?
Believe it or not, the Euler characteristic has even more to offer.
Really?
We've barely scratched the surface of its applications and the different ways mathematicians have proven and explored its properties.
I'm ready to dive deeper.
Oh.
What else can this fascinating concept tell us? So we've been on this incredible journey with the Euler characteristic,
We have.
exploring how this pretty simple idea can be applied to everything from, soccer balls to the entire universe.
I know, it's pretty amazing.
But you mentioned that there's even more to discover
Yeah.
about its properties and its applications.
There is. There's always something more to find. One thing that I think is really cool is how mathematicians have found so many ways to prove Euler's polyhedron formula.
Okay.
We've talked about the formula itself.
Vertices minus edges plus faces equals 2.
Right, exactly. But actually proving it rigorously, that's a whole other challenge.
So there's not just one right way to prove it.
Nope. There are tons of different proofs.
Wow.
This guy, David Epstein, he's a computer scientist and mathematician.
Okay.
He's actually collected a bunch of them.
Really?
Yeah, each one giving a unique perspective on why this formula works.
That's really interesting. It's like there are all these different paths that lead to the same destination.
Yeah, exactly. And each proof highlights these different aspects of the Euler characteristic.
Huh.
What's even more interesting is that some of these proofs have limitations.
Really?
Yeah, or even flaws.
Oh, wow.
And this other brilliant guy, Imre Lakatos,
Okay.
he pointed these out.
So even in this seemingly simple formula,
Yeah.
there's still room for debate and deeper understanding.
Absolutely. Lakatos argued that mathematical concepts, they get refined over time.
Okay.
As mathematicians identify and address those limitations, it's a process of questioning, revising, building upon previous work.
So it's like a detective story.
Kind of, yeah.
With mathematicians piecing together all these clues to uncover the full story of the Euler characteristic.
You got it.
But we focused a lot on the theoretical side.
Right.
What about some practical applications?
Okay.
Does this have any use outside the world of pure mathematics?
For sure. It's found applications in some really surprising places. Like what? Like computer graphics and image analysis.
Okay. I can see how it might apply to graphics, given its connection to shapes.
Yeah.
But image analysis, how does the Euler characteristic fit into that?
So imagine you have an image with different objects in it.
Okay.
The Euler characteristic can be used to analyze the shapes of those objects and distinguish them from each other, even if they're overlapping or partially hidden.
Huh.
Yeah, it's pretty cool.
So it's like using the Euler characteristic as a tool
Right.
to identify and classify objects within an image.
Exactly. And it can even be used for things like facial recognition.
Wow.
Where the shapes of facial features are important for identification.
That's incredible. It's amazing to see how this abstract mathematical concept can be used to solve real-world problems.
It is. And the applications don't stop there. Believe it or not, the Euler characteristic is used in social network analysis.
Social networks.
Yep.
Like Facebook and Twitter.
Exactly.
Now that I have to hear more about it.
So it might seem strange.
Okay.
But think about the structure of a social network. It's basically a network of nodes representing people connected by edges which represent relationships.
So you're saying that network structure can be analyzed using the same principles we've been talking about.
Exactly. The Euler characteristic can help identify clusters and patterns within those networks, revealing things like communities with shared interests or those influential people who connect different groups.
This is blowing my mind all over again.
I know, it's pretty amazing stuff.
It's like this concept has its fingers in every pie.
Yeah.
We've gone from ancient mathematicians thinking about polyhedra to modern applications in fields I never would have imagined.
It really shows the power of abstract mathematical thinking. By taking these complex systems and boiling them down to their essential topological features, we can use tools like the Euler characteristic to gain incredible insight.
This has been an eye-opening deep dive into the world of the Euler characteristic.
Yes.
I'm walking away with a whole new appreciation for how a simple mathematical idea can have such far-reaching implications.
Me too. It just goes to show that math is more than formulas and equations.
Yeah.
It's a language that allows us to describe and understand the world around us in these really profound ways.
I like that. And on that note, it's time for us to wrap up this deep dive. But I encourage everyone listening to keep exploring. There's always more to learn and discover in the fascinating world of mathematics.